Hey there! In this video, we'll be talking about the equilibrium involving dissolution of solids and gases in liquids. First, let's start with solids. I'm sure you have dissolved sugar in water. So this is a picture of sugar being dissolved in water. And as you keep adding sugar, you reach a point known as a saturation point, where you have a saturated sugar solution. So what does this mean? At this point, you cannot add any more sugar at that particular temperature. Let's say the temperature is 25 degrees. At this temperature, you can only dissolve some amount of sugar, and beyond that point, this solution gets saturated. But what if you keep going further? If you still try to dissolve more sugar beyond the saturation point, the sugar will sink to the bottom. But is that all? No. Once you add this extra sugar, it seems to the naked eye that there's nothing much going on. But then there is a lot of activity in the form of a dynamic equilibrium, which means that there is continuous crystallization and dissolution happening, but we just can't see it with our eyes. These sugar crystals continue to go into solution while the crystals in the solution continue to come into the crystal form. Let's try and see an illustration of this. If you had a nano level vision, you'd be able to see the sugar molecules from the solution come into crystallization form and from the crystal go back into the solution. And this keeps happening at exactly the same rate. And that is why it's known as a equilibrium. I have an even better way for you to visualize this. Let's look at that. So here I've made a simulation for you to better understand the process. So this is a beaker of water. Now let's start adding some sugar into this beaker. So we added some sugar here. This is just stirring happening, so don't worry about that. And let's add more sugar. Let's add more sugar. Let's add more sugar. And as you can see, the temperature is constant. It's at 25 degrees Celsius. Now this solution is saturated. At this point, if we add more sugar, we see that the sugar is no longer getting dissolved into this liquid solution. It is now just crystallized at the bottom. So at this point, if we observe what happens, you see that there is a dynamic process. So some of the molecules here are going up into the solution and some of the molecules are coming down into the crystal form. And that is where the dynamic equilibrium happens. So at this point, the rate of dissolution is equal to the rate of crystallization. And that's where we have an equilibrium. This means that there are two processes happening simultaneously at the same rate. And that is why it is a dynamic equilibrium. Since they are at the same rate, they cancel each other out overall, but they continue to happen. That is the main takeaway for you to understand. So let's keep watching. We keep observing that the equilibrium keeps going on, but nothing apart from that happens. So here we've added more sugar. We had more sugar, but now we increase the temperature to 33 and we see more dissolution has happened. So what has happened at this point is the rate of dissolution has increased and the rate of crystallization hasn't. That's why you see that there is more sugar dissolved and there's less sugar in the crystal form. And as we increase the temperature, the rate of dissolution will keep further increasing. At this point, all the sugar which was available here, because we didn't add anything extra, got dissolved into the solution. So at this point, we reached saturation yet again, where all the sugar is dissolved and nothing is left at the crystal form. And if we now reduce the temperature back again, we'll see that the crystal will come back. So as we keep reducing, we'll have more and more crystals coming back. And at every point, if you just stop and observe, if you don't change the temperature, you'll see that the situation remains exactly the same, but the two processes keep happening simultaneously at the same rate. Great. Now let's move ahead. But how can we be sure that this is the case? Because we can't really see what's happening, even with a very, very powerful microscope. Yes, but we can't see a lot of things directly. You can't see gravity, can you? That's why we design experiments to gather evidence. And that's how science works. We can't see things with our eyes, but we can observe them indirectly through experimentation and thought. And that's sometimes better. So in this case, we design an experiment using radioactive sugar and we put that into a saturated sugar solution. And that gives us a very important clue. This is how. So we have this radioactive sugar that we drop into the saturated solution because since this solution is saturated, there's nothing at the bottom at this point. There is no sugar in the crystal form. But when you add this solid radioactive sugar, by the way, this is not how radioactive sugar looks like. It doesn't glow in the dark. It looks like basically regular sugar. This is just for illustration. So when we drop this into the solution, and if you're able to somehow observe that some of these crystals are going into the solution and some of these in the solution are coming back into crystal form, if you have a way to observe that this is a radioactive particle in the solution, then you know, because earlier you didn't have anything radioactive and now you have something radioactive, you know that this crystal form has actually dissolved and some of the dissolved sugar actually went into crystal form, because overall you cannot change the saturation at the same temperature. So that is how we can figure out whether this is dynamic or not. So I have a simulation for you to understand this better. Let's watch it. So here we have a saturated solution and now we'll drop some radioactive sugar inside. So now let's observe what happens. And as you can see, we have some radioactive particles, and obviously this is another animation, but in the real life, what actually happens is we use something known as a Geiger counter. It's known as a GER, it's named after a scientist called Geiger who figured this out. A Geiger counter helps you count the number of radioactive particles by a scientific method, which we don't have to go into right now, but you can actually figure out how much radioactive substance is inside the solution and how much is not inside. So since before we didn't have anything and now we are able to detect something, we know that some of this have actually gone here and some of these have actually come down here. And this is how we can imagine the way it looks. As time passes, more radioactive particles go into solution and more of the non-radioactive particles come into crystal form. But after a particular point, you'll reach an equilibrium beyond which nothing much changes and the two processes keep going on in the same rate. Great. I hope that was clear. Let's move ahead. Now let's talk about gases in liquids. This is a bottle with carbonated water, which is basically carbon dioxide dissolved in water under pressure. I'm sure you've seen this, a soda bottle. What happens when you open the bottle? You see a huge fizz. But why? Have you thought about that? So the reason why this happens is the bottle before was under a lot of pressure. It was under high pressure because the gas that was inside was sealed with a lot of pressure, and that is pushing on to this liquid, and that actually increases the solubility of this carbon dioxide within this liquid. But when you open the bottle, what happened when you suddenly exposed this bottle to atmosphere, which has a much lower pressure compared to the bottle before? That has reduced the solubility of carbon dioxide, and that is why a lot of carbon dioxide gushes out of the solution. That is very similar to how the sugar actually crystallized out of the solution after the saturation point. And that was dependent on the temperature. And this is dependent on the pressure. Quite a similar scenario. And the law which governs the solubility of CO2 in the liquid is known as the Henry's law. And this law says that the mass of a gas dissolved in a given mass of a solvent at any temperature is proportional to the pressure of the gas above the solvent. If that was not completely clear, I get it. Here's how we can make it clearer. So imagine there's 100 grams of water and we have dissolved about 0.1 grams of CO2 at 1 atmosphere of pressure. If you increase the pressure by 10x to 10 atmospheres, then you increase the solubility too by 10x. And that is what proportionality of pressure to solubility is. If you increase the pressure by any multiple, you'll increase the solubility by the same multiple. So in mathematical terms, you can say the mass of the gas divided by the mass of the solvent is proportional to the pressure of the gas. Or could also say that the concentration of the gas, C is concentration, is proportional to the pressure of the gas. That is the Henry's law. So we learned about two things, solids and liquids and gases and liquids. In solids, we know that the solubility is constant at a given temperature. In gases, we see that the concentration of gas is proportional to the pressure of the gas or the liquid at a given temperature. So overall, in physical equilibrium, we've observed 5 characteristics that we can summarize. If we take any physical equilibrium example, like the one of sugar solution, we see that the first requirement is that we need a closed system. There should not be any external influence on the system, and the system should be completely isolated from external influences to maintain the equilibrium. And all this we're talking about is when the equilibrium is achieved. When the equilibrium is achieved, first you need to have a closed system to maintain it. You will have a dynamic balance. That means both processes occur at the same rate, which we spoke about multiple times. The system appears static, but is actually in constant motion. And we also observe that the properties are all constant. All the measurable properties are constant. Temperature, pressure, everything remains constant at the physical equilibrium state. And we also observe that the characteristic parameters are of constant value. at a given temperature, like the paper pressure, solubility. At the given temperature, those values remain constant. And we also observe that it is an excellent indicator of the extent of the reaction, which means that at this point, if I can calculate the concentration of the solution, then I can tell you exactly how much of the reaction is remaining before it reaches the equilibrium point. Perfect. And that is all about physical equilibrium, and especially about solids and liquids and gases. Hope you learned something today. I'll see you next time.